All right, so now on to curvature. Now, curvature is a very important topic because it gives us a way to actually measure how sharply a smooth curve turns. For example, we know a circle has constant curvature, and the smaller the radius of the circle, the greater the curvature. Right, so let's look at this, right? In fact, it actually turns out that the curvature is the reciprocal of the radius of the circle. So let's look at a picture. This is figure 3.6 from the textbook. Notice that where we have the larger circle tangent to our curve, the curve is slower to change. And where we have the smaller circle, we have a more abrupt change, right? The graph is sharper. So we say that the curvature of the graph at a point is actually the same as the curvature of the inscribed circle. And to define that, well, more precisely, of course, if C is a smooth curve given by the arc length parameterized curve, R of S. So notice here that we have to parameterize our curve using the arc length parameterization. Then the curvature, which is denoted by the Greek letter kappa at S, is given by kappa equals the magnitude of dt ds, which we can write a little more succinctly as just t prime evaluated at S. Recall that t is the unit tangent vector. So we have a few things that we have to think about if we're using this formula. This formula kind of inconvenient, right? Because we have to pre-parameterize the curve to get it in terms of its arc length. But fortunately for us, there are other formulas that are, can I say, at least a little bit simpler? Okay, so let's look at some alternate formulas. If C is a smooth curve given by the vector value function R of t, the curvature kappa of C at t is given by, it turns out, the magnitude of the unit tangent divided by the magnitude of R prime of t. If C happens to be a three-dimensional curve, then the curvature can also be found by this formula. It's the magnitude of the cross product of the first and second derivatives of our vector value function divided by the magnitude of the derivative quantity cubed. Finally, if C is the graph of a function y equals f of x, and actually this is the one that's kind of used in practice that I can think of, and both y and y double prime exist, then the curvature kappa at any point xy is given by the absolute value of y double prime divided by the quantity 1 plus y prime squared, and all of that to the 3/2. So those are 1, 2, 3, 4 formulas for computing the curvature. So let's just do an example of kind of one of the more wicked ones, i.e. a three-dimensional vector valued function. So let's determine the curvature for the function defined by the vector t, 3 sine t, 3 cos t. Well, it's pretty easy to find the tangent vector, right? R prime of t, just take the derivative of each of those terms. Derivative of t is 1. Derivative of sine of t is 3 cosine t. Derivative of 3 cosine t is minus 3 sine t. And we can find the magnitude of that. It's just going to be the square root of 1 squared plus 3 cosine of t squared plus negative 3 sine of t squared, which is going to give us square root of 1 plus 9 cos squared t plus 9 sine squared t. You can factor out the 9, you get cos squared plus sine squared. So that's going to give us the square root of 1 plus 9, or the square root of 10. The next thing we need is the unit tangent vector, but that's simply found by, right, taking r prime and dividing by the magnitude. So I'm going to get, after plug and play, right, 1 over root 10, 3 over root 10 cosine of t, negative 3 over root 10 sine of t. Next, we need to find t prime of t, right? We need the derivative of it if we're going to use equation 16, which I'm going to do, because I think it's probably the easiest one in this particular case. Okay, so the derivative of t is going to be, well, 0 for the first term, derivative of cosine. So I'm going to get a negative 3 over root 10 sine t, and a derivative of sine being cosine, negative 3 over root 10 cosine t. So the magnitude of this vector is the square root of 0 squared plus the quantity negative 3 over root 10 sine t squared plus the quantity negative 3 over root 10 cosine of t squared. And that's going to give me square root of 9/10 sine squared t plus 9/10 cosine squared t, which is just the square root of 9/10, which is 3 over root 10. Now at this point you might be going, well, dang, Professor, you made us every single time rationalize, get rid of the square roots in the denominator. And I'll say, sure, but we're not done yet, so might as well wait till we get done and do everything at once. Finally, the curvature is then kappa is equal to the magnitude of t prime of t. Apologies, let me fix that handwriting. Divided by the magnitude of r prime of t. We've calculated both of these. Let me circle them so it's easier. So we've got the magnitude of t prime of t. That's the one we just did. And we have the magnitude of r prime of t. That's the one up here. And so that's what we plug into our equation. So we have 3 divided by root 10 divided by root 10, also known as 3/10. So our curvature is 3/10. Excellent. Let us do one more example. Let's find the curvature of the curve defined by the vector valued function. R of t is t squared times I plus t times k. Let's do the other equation this time. Let's use the one with the cross product. All right, so let's try that one for a change. Let's use equation 17. So r prime of t is 2t times I plus 1 times k. And then the second derivative is just going to be 2 times I. And, you know, if you look at those formulas, you might see why we decided to just go with the cross product one. So the cross product of r prime and r double prime is matrix I, J. K is the first row, 2t, 0, 1 is the second row. and 2, 0, 0 is the third row. So if we do all of our work like we've been doing, right, what goes in the first matrix? You should pause and think about that before I do it. So we're going to have 0, 1, 0, 0 plus, nope, minus. What goes in the second matrix? Again, you should be thinking about this. 2t, 1, 2, 0. And finally, the third matrix times k. And what that gives me is 2 times j. So for our magnitudes that we need for the formula, okay, so the magnitude of this cross product is going to be, well, it's the square root of 0 squared plus 2 squared plus 0 squared, which is just 2. And the magnitude of r prime is going to be the square root of 2t squared plus 0 squared plus 1 squared, or square root of 4t squared plus 1. So now our curvature is the magnitude of the cross product divided by the magnitude of r prime, and that cubed. So I get 2 over 4t squared plus 1 to the 3/2. And that's the answer. And that's it for curvature. So next time we're going to talk about normal and binormal vectors. And until next time, have a great one.